What can you expect today? So I will represent to you a methodology that we developed to efficiently fuzz automotive software. I will explain this methodology first theoretically, and then I will show you how we use this using our tool CI-Fuzz. But of course, you can also use the same approach with other tools. After I show you how to use it with CI-Fuzz, I also will give some tips how you can use the same methodology to fuzz your own software with the tool of your choice. Also in this webcast, we will make use of the Fuzz data provider, which we will see later. I will not explain all the details of this tool, but I can strongly recommend you to check out this tool because it's very useful for fuzzing. But I will tell you a little bit about this, but as I said, I recommend that you also take a look at this yourself. So a little bit about me. My name is Teuchert. I'm a customer success engineer at Code Intelligence. Before I was working for Code Intelligence, I worked as a penetration tester and information security consultant. And as my master thesis, together with others, I developed and worked on the feedback-oriented grammar fuzzer called Nautilus. My responsibilities at Code Intelligence are to show our customers the value of our product CI-Fuzz, and I onboard our customers so that they get the most out of our product. And together we identify the best approaches to fuzz the code of our customers. In the last weeks, I was working on a couple of automotive projects, and there we encountered some problems where I want to show you today how we overcame those problems. Let's first start with a very short recap on feedback-based fuzzing. This will be quite short, so if you are not familiar with feedback-based fuzzing at all, I also recommend that you check out, for example, our blog about the magic behind feedback-based fuzzing. But basically what feedback-based fuzzing is, we have a system that we want to test, and we have the fuzzer, and the fuzzer executes the system, and it feeds a randomly generated input to our system. And then the system under test is monitored so that we can see if the system crashes or if it shows any other unwanted behavior. And the great thing about feedback-based fuzzing is that our fuzzer also gets some coverage information back. So our fuzzer actually, whenever it executes the test system with an input, the fuzzer gets information about what kind of code was executed. So which path did our program take during execution. And for fuzzing, generally speaking, the goal is to achieve a very high code coverage, because if you achieve a high code coverage, then the chances are high that you can find bugs that are hidden anywhere. If you only test your system with like the same test case that you already know, then the program will always take the same path and will always execute the same code, but there might be some bugs hidden to the left or to the right of this path. So by getting this feedback, the fuzzer can learn basically how he should mutate inputs in a way so that when the system is executed with these inputs, new code paths are executed. And in the end, this will lead to a high code coverage, and this can uncover a lot of bugs. And in our approach, what's important for you is we will make use of this like learning mechanism of our fuzzer. So this feedback that our fuzzer gets makes it like an AI that can learn how to change inputs, and it can also learn different things. So let's talk about the challenges that we encountered when working with automotive customers. So we had like three main challenges. One was that the automotive software often is very low-level code, and it also often has some code that only runs on specific hardware, for example, some sensors that measure values and report it back to the software that we want to fuzz. So when we want to test our software, we cannot compile these hardware dependencies on our test machine, because our test machines usually need to be very strong machines that can execute our software very fast, and we cannot test on the actual hardware. So this was one problem. Another problem was that generating good fuzz tests can take a lot of time. As I said earlier, usually with fuzzing, you want to achieve a very high code coverage. So one way would be to think about fuzz tests that execute all the possible functions and maybe also all in the right order, so that your inputs can execute all the code that you want to test. This can take a lot of time if you want to do this manually. Also, this gets even harder if you have stateful applications, because then when creating your fuzz tests, you really have to think about, okay, what function, in which order do I call my functions so that I can move my application in a specific state that I need to execute this function. So what we did to overcome these problems was we tried to automate as much as possible, so that you save a lot of time. And at the same time, with this automated approach, in the end, we wanted to have a fuzz test that generates a very good code coverage. So in the end, we are using, again, the feedback that our fuzzer gets, so that our fuzzer can learn actually what kind of tests to execute. You will see this later in a little bit more details. But our approach consists of these two parts. First, we created mocks, so like simulations for the hardware or third-party dependencies that we cannot compile on our testing machine. And the good thing is that these simulations for these functions, they don't return just static values, but they return, or they use also fuzz data. So this way our fuzzer can get feedback on what kind of data these functions should return. And for our fuzz test, we also use fuzz data so that our fuzzer can learn by itself which functions to call in which order. So let's take a closer look. How does it actually work? So here in the middle, you can see the module that you want to test. So this is the code that you can actually compile, for example, on a Linux machine. This code has a public API. These are all the functions that you want to test. So these are the functions that your fuzzer should call with random inputs. But then below this, you also have the hardware-dependent APIs. So these are the functions that we cannot compile on our testing machine. But when we run our software, this software will need some return values from these functions. So it needs to call some functions. So we have to implement these functions in a way that we can run it on a Linux machine. And at the same time, these functions can simulate how the actual hardware would behave. And we do this by connecting both of these with our fuzzing engine. So this connection up here is like the normal approach. Our fuzzer, whenever it calls these functions that we want to test, it supplies fuzzing data as the arguments that we call these functions with. So if we have a function, our fuzzer just tries to execute it with different inputs, and then we see if our module behaves weirdly or unexpected. And at the same time, whenever our module makes a call to one of these functions that are hardware dependent, we have our own implementation of this function. And this function then also returns fuzzing data. So our fuzzer also injects his input into the return values of these functions that we normally could only execute on specific hardware. So this way we can test this module under all the circumstances. We can test for all the possibilities how the functions can be called. And at the same time, we also simulate all the possibilities how the hardware below might react. And this is how we automated our approach. So actually to generate a fuzz test, to test our public API, we just need to fill in a simple configuration file, like for example, an Excel sheet. And from this Excel sheet, we can generate automatically a fuzz test that can achieve a great code coverage. And also we only need one Excel sheet from which we can generate the implementation of our mocking library, of the mocked functions. Let's take a look how these Excel sheets look like. So here we have a table for the functions that we want to mock, that we want to simulate. So for example, we could have a function called getX, and this function usually returns an integer. So one way to implement this function for testing could be, okay, just getX, whenever it is called, it just returns 0. But for our fuzzing approach, we want to achieve a high code coverage. We want to simulate how this function could react on a real machine. So we want to return fuzzing data. So we annotate this here, saying that, okay, this function getX should return an integer. And when we, from this table, when we use our script to automatically generate the implementation, then we get this function, int getX. And as you can see, also this function does not do anything rather than just returning a value. And here we are using the fuzz data provider that I talked about before. What this does basically is from our fuzzing data, we consume an integral. So the fuzzing data usually is just a buffer of bytes, but we want to return an integer. So from our fuzzing data, we take one integer, and whenever this function is called, we just return the integer. So if we call this function twice, it might return 2 different values. And then another function that we might want to simulate would, for example, be getBuff. This function also returns an integer, but it also gets a pointer to a char array. So it might be that this function, whenever it is called, not only returns an integer, but it can also change the memory that is, or the data that is stored at the location where this pointer points to. So for example, if this pointer usually points to an array of 16 bytes, we can annotate it like this and say, okay, this points to an array of 16 bytes. And when we generate our mocking function, it will result again in a function that returns an integer using the fuzz data provider. But also we use the fuzz data provider to write 16 bytes. So first we take 16 bytes from our fuzz data, and we write these bytes at the location where B points to. So we overwrite everything that's at this position, and we overwrite it with fuzz data. So because when this function would be executed on the actual hardware, it also might change the memory that's stored here. So this is how we create our mocking library to simulate all the external sources, all the external inputs that our software depends on. Then we also want to create a table for generating a fuzz test that gives us a lot of code coverage. So for this, we need a table that contains all the functions that we want to fuzz. So all the functions that we implemented and where we want to check if they are executed, do they behave in the correct way, or do they crash or behave in an unexpected way. So in this table, we are not interested actually in the return values. but we are more interested in what kind of parameters do these functions get, because we want to see if they are called with any combination of parameters, does our program crash or not. So for example, this function called foo is a function that as the first parameter, it takes a pointer to a char array, and the second parameter is an integer called leng. And most likely this, this char array has a dynamic size, and the size of this array is given in the second argument. So we can annotate this here saying, okay, the data parameter just contains some data, and the leng parameter shows us the size of this data. So when we generate our fuzz test from here, whenever the function foo is called, our fuzzer takes a random size, and it creates an array of this size and fills it with random data. And then with these parameters, the function foo is called. Another example would be a function called bar that just takes an integer. So we can just take a random integer from our fuzz data and call this function with this integer. So when we generate a fuzz test from this Excel sheet, then we will have a fuzz test that when it runs, it picks a random list of functions, and it calls them in a random order. And whenever one of these functions is called, it is also called with random parameters. And this will result in a fuzz test that covers all the functions in a random order. Our fuzzer by itself finds which combinations of functions are good and which are not good. And at the same time, we also simulate all the external inputs that our program depends on. As I see, there are some questions already. I will answer the questions in the end. So, of course, you can ask your questions right now, but in the end, we will have a Q&A. So let's get even more specific. So what are the steps that you need to do with this approach? Actually, it's just 3 steps. First step being you need to identify all the dependencies that need to be mocked. So which kind of code you cannot execute on your testing machine, and which kind of functions you need to create an implementation for. Luckily, this can be done automatically in the most cases. And then from this, when you identify this, you need to fill in like some documentation about these functions. As I've shown earlier, you need to document what kind of return values these functions that you need to implement, what kind of return values they expect. And lastly, you need to fill in an Excel sheet for the fuzz test. So you need to fill in a sheet where you document all the functions that you want to test, and there you document all the parameters that these functions expect. And with this, you can generate your fuzz test. So let's see this in action. So since I cannot show you any code of our customers here, I created a sample project with a little bit with some source code. So we have like 4 modules here. We have a crypto module, GPS module, key management module, and time module. And we have just a small C project. And so, for example, this GPS module has a few functionalities like get current position, or set and get destination position might be used for navigation, and initializing the crypto module. So if you would like to fuzz this project, we will start doing it the manual way, and then I will show you how we can very fast generate a good fuzz test with our approach. So I'm using CI Fuzz. This is why I can use our plugin here to generate a fuzzing project first. So let's call it Automotive Fuzzing example. This project is using CMake, so we don't have to change anything here. What this will do is it will build all of our code here as a static library. And while it is doing this, it will also insert instrumentation. And this instrumentation is very important for feedback-based fuzzing, because this instrumentation allows our fuzzer to get the feedback about which kind of code was covered and what was not covered. So when I build it now, as I said, the static library will be built, and it will be built with instrumentation. Okay, so this is done. So the next step would be we want to start fuzzing. So we could start picking any of these functions and create a fuzz test for this function. So for example, we could say, okay, this function here looks interesting. Let's fuzz this function. From our plugin, we have this button fuzz this function here, which I'm going to use. And what this did now is it just created a scaffold fuzz test here, and we are using libfuzzer. So what this does, it just already included all the needed includes to run this function. And then we have these two functions that are important for the libfuzzer. So the fuzz init function is called once when you start your fuzzing process. And this can be used for any initial setup if you need to bring your module in a specific state for fuzzing. But actually for this simple example, we don't need this, so we can remove it. What's more important is this fuzz function. And this function is called by libfuzzer in a loop. So this is called many, many times. And every time this function is called, the fuzz data is provided with this pointer. So this variable data will contain our fuzzing data, and this variable size will tell us how much fuzz data we have. So what you would do is, if you want to fuzz this function, you would want to call this function with an instance of an object of GPS position, but you would want to fill this object GPS position with fuzz data, so that when this function is called, it's always called with different objects. So to do this, let's first take a look what this GPS position object actually is. And let's take a look at it. And we see it's a struct, and it's a very simple struct. So it's a struct that just has 6 members, all of type uint8t. So to fill this struct with our fuzz data, we just need 6 bytes of fuzz data, and we can write 1 byte at each of these members. So let's go back to our fuzz test and create our fuzz test. So first we want to create one instance of this object, GPS position. Let's call it position. At first, initialize it with 0. And now we want to fill this object with our fuzz data. But first, as I said before, we need 6 bytes of fuzz data. We have to check if we actually have 6 bytes, because we might have less than 6 bytes of fuzz data. So let's first check if size is actually greater than or at least equal to 6. And if this is the case, then we can write our fuzz data to our position object. So we can just, for all the members, write 1 byte from our fuzz data to this object. So 1, 2, 3, 4, 5, 6. So this way, we fill the object with the data that we get from our fuzzer. And lastly, last important step, is to provide this object when we call this function. And if we take a look at the function declaration, we actually need to provide a pointer to our object. So now when this is called in a loop, we create different objects with different data that will, so this function might behave in different ways. So now we can run our Fuzz test. To do this, we need to compile our Fuzz test together with the static library that we compiled with instrumentation, and this needs to be linked together. To do this, we have to configure the bit flags here. This is already, a lot of it was filled in automatically already when we clicked on the Fuzz this function button. But generally what it does, we have here our static library that we want to link with our Fuzz test. And then we have some include directories. One directory was not included automatically. We also need the GPS module source directory because to call the function, we need to have access to this header file. So GPS module source. Because if I go back to our Fuzz test, we are including this file here because we are using this function that is declared in this module. So let's go back. We have this set up. And then here we can start our Fuzz test. So now when I click start, our instrumented library will be linked together with our compiled Fuzz test. So, but as you see here, it fails. And let's take a look why it failed. And oh, actually, I did a problem. Okay, we have some undefined reference errors here. So these are linker errors. And this means that we have some functions here that are declared but are not defined. So let's search for this function, for example. So as we can see here, it is declared as an extern function. Because as the name might suggest, GPS_driver, this might be a function that is only implemented on a driver that only runs on specific hardware. So if we want to run our test on our Linux machine, we would have to provide an implementation for this function. So an implementation for this function might look as easy as this. For example, we have this function, and then this is still big enough. So this function, we can just say return 0. So whenever this function is called, it returns 0, and that's it. But this is not very helpful when fuzzing, because we want to find all the cases that can happen. So we want to use our fuzz data to be returned here. So what we need to do is we need to find all the functions that are declared in our module but are not defined. And then we need to implement these functions to return our fuzzing data. To do this, we wrote a simple Python script that I'm going to show you. So here we have our script called gen templates. And when I run the script, I have to provide it with all the source code that it should search through, and it will search through all the source files, and it will create 2 Excel sheets. In one Excel sheet, we will have all the functions that are declared but not defined. So these are all the functions that we have to mock, where we have to create an implementation for. And the second Excel sheet will actually be with all the functions that are not only declared but also defined. So these are all the functions that we implemented So these are all the functions that we want to test. So the second Excel sheet will be important later when we want to create our Fuzz test. So what I'm doing here is, let me show you the folder layout. So we are in this folder here, and our code is all in this modules folder, and then we have different module folder names, and then we have the source folder here. So I just pointed our script to the same folder, and then we want to give it all the modules, and then we have the source folder, and we want to that it reads all the .c files and all the .h files. So when I run this now, it creates 2 Excel sheets. So this was the script that we executed, and it generated 2 Excel sheets here. One is for our mocking library. Well, this is a little bit small, but it says test gen mocks. And one is for our functions that we want to test gen functions. So let's start with the test gen mocks Excel sheet. So it identified 4 functions that are declared but not defined. So now we want to document what these functions return, so that we can generate an implementation for these functions that returns Fuzz data. So for example, here we can say this function, it returns an integer and an integer of type int. The second function also returns an integer of type int, but the third function, for example, it also returns an integer, but it returns an integer of type uint8t. And the last function also returns an integer. So this is information about the return values. Then we see this function also gets pointers to some data. So it might change the data here. So we want to change the data as well with our implementation. So now it would be important for us to know how much data it points. So how large is the buffer that it points to. This could be documented in your API documentation, but for now, for this example, we will search for this function in our code to have a look at what kind of buffers are provided here. So let's search for this function in our code. This was the function, and it is used in the C file. Here the function is called, and the first parameter is an array of size 12, because it's a uint8 array with 12 members. And the second one is an array of size 64. So with this information, we can go back to our Excel sheet and we can say, okay, the parameter position as bytes, we want to write bytes to this address, and we want to write 12 bytes. As we saw, it was 12 bytes large. And the second parameter, called hmac as bytes, we want to write bytes to this parameter, and we want to write 64 bytes. And then for this second function, we also see it takes a lot of pointers, but many of these pointers are constant, so we cannot change the data here. So this is constant, and this. Only thing that we can change is the last buffer, which is another buffer called hmac. And we could check the code, and we would see that this also points to a buffer of 64 bytes. So we write bytes 64. And this is everything we need to fill in for our functions. And now we can save this Excel sheet and close it. And we can use another script to, from this Excel sheet, generate our mocking library. So We have another Python script. This one is called gen test. And this script can be used in two ways. It can be used to create a mocking library, or it can be used to generate a fuzz test. So first, we want to use it to create a mocking library. So what we need to do, we need to provide it with the Excel sheet that we just filled in. And this Excel sheet is in the folder that we just came from. So this gen template folder, and it's called, gen template, and it's called test gen mocks.xlsx. And now the last parameter is where we want to place our mocking library. So I prepared a folder for this. Here in our project, we have this fuzzing folder, and we are actually currently in this folder with our script. And we have this mocking library here, where we also have the fuzz data provider header file that we make use of. And let's just put our mocking library in this folder. So just it's one folder up, and then in the mocks folder. So let's execute it. And as you can see here, we generated two files, mocklib.h and mocklib.cpp. Let's take a look at these two files. So the mocklib.h file, it included the fuzz data provider header, and then it again declares the four functions that we want to implement. And it also, we have two helper functions. This function is not important for now, but this mocklib setData function is important because for our mocking library to be able to return fuzz data, we need to give it access to the fuzz data. So this function is like used to initialize our mocking library. I will show you how to use this function in a minute. So let's take a look at the implementation of these four functions. So here we have the implementation of the two helper functions. And down here, we have the implementation of the four functions that we need to mock. As you can see, for example, this function does not do anything. It just returns an integer. And we take this integer from our fuzz data provider with the function called consumeIntegral. We can, from the byte stream that we get from our fuzzer, we can just take an integer. And with the same function, we can also take a uint8 variable. So when this function is called, we take an integer from our fuzz data and return it. Then we have these two functions that not only return an integer from our fuzz data, but they also write some fuzz data at the position where these pointers point to. So for example, this pointer, as we saw earlier, it pointed to a 12-byte array. So we take 12 bytes from our fuzz data and we write it at the location where this pointer points to. And we take 64 bytes and write it at the location where this pointer points to. So this is how we automatically generate the implementation for these functions. So next, what we need to do is we need to give our mocking library access to the fuzzing data, and then we can run our test again. So we need to include the fuzz data provider in our fuzz test. This is our fuzz test from before. We also need to include the mocklib.h because we will have to call the mocklib setData function to give our mocking library access to the fuzzer data. And we will have to call this function here. First, we need to create a fuzz data provider. Let's call it fuzz data provider. And this fuzz data provider has access to our fuzzing data. So we give it just the pointer to our fuzz data and the size. And next, to give our mocking library access to the fuzz data, we call this mocklib setData function, and we give it a pointer to our fuzz data provider that we just created here. So now also our mocking library has access to our fuzzing data. So with that being set up, there's only one thing left. We also, when we compile our fuzz test together with the static library, we also need to compile our mocking library that we just created, the library with the implementation of the functions that we need to simulate. So these are mocking library is in the folder fuzzing mocks. So fuzzing mocks mocklib.cpp will be compiled with the rest and linked. And then also to be able to use the fuzz data provider and the mocklib header file, we also need to include this folder in the include directories. So fuzzing mocks needs to be added here. Fuzzing mocks. So now when I run this test again, it will not only compile our fuzz test, but it will also compile our mocking library. So let's run our test again. So now, yeah, as I said, it's compiling all the three components and linking them together. And we have our fuzz test running. So as you can see, we have a little bit of coverage. We have a very high execution count, which is normal because we are just testing one small function. So there's not a lot of code that is executed. Also, our fuzzer only found 9 different inputs that found different paths in our code. If we take a look at the coverage, we can also see what code we executed right now. So this is our fuzz test. So we executed our whole fuzz test, but that's not that interesting for us. Also, it's not that interesting how much we covered from the fuzz data provider or from our mocking library. But what we are interested in is a high coverage in the implementation of our functions. So, for example, this is the GPS module .c file. Here we have the function that we are executing, and everything red has not been executed yet. So as you can see, even from this function, firstly, we are only executing this one function, and secondly, we are also not entering this block here, because maybe we need to execute some other functions before that to set our program in the correct state. So an approach to increase our code coverage now would be to, again, create these fuzz tests for all the functions that we have, and maybe also think about interesting tests where we call functions in an interesting order. But this takes a lot of time, so we want to do this automatically. So let's stop our fuzz test. And if you remember, our first script generated 2 Excel sheets, one with the functions that are declared but not defined, and one with the functions that are actually defined. So these are the functions that we want to test. Let's open this Excel sheet. And as you can see here, for example, here we also have the function getCurrentPosition that we wrote our fuzz test for. But we also have all the other functions in our module. So now we want to create a fuzz test using all these functions. A fuzz test that when it is executed, it picks these functions in a random order and executes them with random input. So now the return value is not important for us, but the only thing that is important for us is what kind of parameters do these functions take. So, for example, the first function here, called cryptocalculateHMAC, it, as a first parameter, it takes a pointer to an array. Second parameter is length. So most likely this will be an array of variable size, and this one will define how long it is actually. So what we can do here, we can tell our next script that this is an argument that contains the data, and the size of it is defined in this variable. So when our fuzzer executes this function, it will randomly pick a size and then create an array of this size and fill it with random data, and this will be given as the message. The last parameter of this function is a pointer to an object of type crypto_hmac. So we don't know what this is actually. So let's take a quick look what kind of object this is. So let's search for this function in our code. And here we have the function. Here we have the crypto_hmac object. So let's take a look what this is. And we see it's a struct, and it's a very simple struct. So again, for us, it's not very important what's in here in this struct. It also doesn't matter for us right now how long this is. Only thing is it's a struct that we can just override with our fuzzing data. If this would be a struct where there are some pointers that when they are overwritten with fuzzing data, this might get problematic. So in these cases, some manual effort is still needed. But if it's a struct like this, so simple, we only need very little effort here in our Excel sheet. So we can just say, okay, this is a pointer to a struct, as we can see here. It's a struct pointer, and the struct is of type crypto_hmac. So now when this function is called, we have this data buffer, and we also will create a struct of type crypto_hmac, and we will just override it completely with our fuzzing data. So then we can continue. So this next function, it takes a parameter of type crypto key. So we can just write arg struct crypto key. So that's it. Then we have a parameter of type crypto nonce. So arg struct crypto nonce. The next one, again, it takes a pointer to an array and length. So this is again this combination of arg data, and also it's called the same, so we can just copy from here. Same. And even the last parameter is the same as the function before. So the next function, again, it gets a struct of type crypto key, so we can copy from here. And the next one, we have again a struct, but this time it's a pointer to a struct, so arg struct pointer, and type is crypto nonce. And then we have the next function. Again, we have a buffer pointer with a length. So again, we have this arg data and size combination. Next function takes a pointer to GPS position. So we have arg data, arg struct pointer, and the type is GPS position. Next function, we have a pointer to a uint8 array and a length. So most likely this will be again a combination of arg data and size. So arg data, and here we can use it from here, arg size. The next function is the same, so here we can also use the arg data and size combination. And the last is again a struct of type GPS position. So for these functions, they don't take any parameters, so we don't have to fill anything here. So this should be it. We can save our Excel sheet, and then we can use our second script to generate our fuzz test from this Excel sheet. So let's close this and open our terminal where we have our Python script. So this time we want to use it to generate a fuzz test, not a mocking library. Again, as the second argument, we need to provide the Excel sheet that we just filled in. So this time it's the functions Excel sheet. And again, we need to tell where we want to save it. So we are currently in this folder. So let's just place our fuzz test in this folder. So just the dot, I tell it, okay, just save the fuzz test here. And I execute it. And as you can see here, we have a fuzztest.c, which was generated by our script using the Excel sheet that we filled in. So let's open it. And we can just copy all of this and use it as our new fuzz test. So this is our old fuzz test, and we just replace it with the new one that we generated. And let's take a closer look what we generated here. So the surroundings are very similar. We also have automatically included the fuzz data provider and our mock library. Then here we have the declaration of all the functions that we want to test. And then down below we have this fuzz function that we used earlier. Again, we have the initialization of our fuzz data provider, and we have we set up our mocking library. And then here comes the interesting part. We have a for loop and a switch case. So what happens here is, well, we take an integer from our fuzzer, and with the fuzz data provider, we can take an integer from 1 to 100. And this is the amount of iterations that we will do for this for loop. So for example, our fuzzer could pick, say, okay, we will do 25 iterations. And then for each iteration, we will pick another number, again, using the fuzz data provider, pick a number between 0 and 15. And this will determine which of these switch cases we will go into. And each of these cases will lead to the execution of one of the 16 functions that we want to test. So for example, for the first iteration, our fuzzer could provide a 2. So this will lead to us executing the cryptosetNonce function. And then for the next iteration, it will return a 1. So then we will execute the cryptosetKey. So this means that our fuzzer actually guides which functions are called in which order. And using the feedback, then the fuzzer can decide, okay, or it can identify, okay, first calling this function, then this, actually finds me new paths in the execution. And calling this and then this does not give me any new feedback. So this is how we use the fuzz data, how we use the fuzzer, the learning mechanism of the fuzzer to like dynamically generate interesting test cases. So one last thing we need to do to execute this fuzz test is we need to include 2 more header files from our modules, from the crypto module, because we need to know what this crypto key object is, for example. And we also need to include from our GPS module to know what the GPS position object is. So we need to include these 2 headers, and then all should be fine. And we can execute our fuzz test again. So we changed our fuzz test, and let's run our new fuzz test, and let's see what kind of coverage we generate. So again, it's building our fuzz test together with our mocking library, and then it links all of this together with the instrumented library that is all our source code compiled. So if we compare this now, this was our last run, and this is our new run. We see that we have a much higher coverage. We also, our fuzzer found many more interesting inputs that trigger new paths. And if we take a look at the code coverage, we can also see that we have found in some of the files we actually have 100% of coverage. Let's see one second. Okay, here you can see the coverage for all of the files. So for example, the time module.c is one of the self-implemented functions. We actually have 100% of coverage here. Key management module 100%. And we have some files where we don't have 100% yet. So we could see maybe if we leave our fuzzer running, he will find the paths to trigger the last percents, or we might have to take a look here and see which code did not get triggered yet, and how we can change our fuzz test. But we already, without any manual effort, we achieved a very high code coverage. And that's it for the demo. Let's go back to the slides. So what did we do? So with a few steps, we just created a fuzz test that, at least for our example code, achieved a very high code coverage. And the good thing is we didn't need to understand exactly what does this module do. We just created a fuzz test where the fuzzer can identify everything on its own. So what did we do actually? First, we had to identify all the functions that we need to simulate, that we need to mock. We did this with our first script, and then we had these two Excel sheets. Then we filled in the Excel sheet for all the functions that need to be mocked. And from there, with the second script, we generated our mocking library, where these functions return our fuzzer data. And lastly, we filled in the Excel sheet for all the functions that we want to test, for all the functions that are from our own implementation. And we generated a fuzz test where all these functions are called in a random order and with random input parameters. And as a result, we had a fuzz test that achieved a high code coverage. And at the same time, we also simulated all the external return values that our module expects. So did this fix our problems that I stated before? So the first problem was that we could not execute or not compile our fuzz test because we needed some implementation for functions that we cannot execute on our test machine. By filling in the Excel sheet for these functions, we could automatically create an implementation for these functions that simulates these return values for the external dependencies. So we fixed this. Also, we did not have to create fuzz tests for all the functions manually, but as you saw, we just had to fill out this one Excel sheet for all the functions and the input parameters that they require. And from this, we were able to generate a fuzz test that tests all of our functions. And lastly, also, since in our fuzz test, our fuzzer decides in which order to call these functions, with the feedback that the fuzzer gets, it can automatically identify how to order the functions to like catch all the states of our application. So we also checked this problem. So one last thing now is, so how can you apply this to your own code? So I showed you how to do it with our project CI Fuzz, but of course this same approach can work also with any feedback fuzzer of your choice. What you need to do is first you need to document your APIs in a structured way so that you later from this can generate your mocking library and your fuzz test. So what you need to do is for all your dependency APIs, you need to document the return types. What kind of data types does your API return? And for your public API, for the functions that you want to test, you need to document what kind of input parameters does this API expect. And from this, you could manually create a mocking library, but of course it's much faster, much more efficient to create a script that can parse your documentation and create this mocking library automatically. So in a way that these functions are implemented to return values that are filled with Fuzz data. And I strongly recommend to make use of the Fuzz data provider, which is open source and included in the LLVM project. So this can make it very easy to return data of different data types. And lastly, or next, you need to create a script that parses your public API documentation to create a Fuzz test that calls all your functions in random order. And whenever these functions are called, they also need to be called with random parameters that are filled with Fuzz data. Again, here the Fuzz data provider can help a lot. And then last thing is you run your Fuzz test together with your software and together with a created mocking library, and you only have to wait for the bugs to appear. All right, so thank you very much. I hope this was helpful to you. If you are more interested in fuzzing, you can learn more about fuzzing in our Fuzzing Academy. You can also read more about fuzzing in our blog. We also have some blog posts about automotive fuzzing. And we also this year released an open source Java fuzzer called Jezza, which you can also try to use. So yes, now I'm ready to get to your questions. Here I just have another slide with the general approach. So if you have any questions but don't remember exactly how this approach worked, maybe this helps you. So let's take a look at the questions that we had. So let me see where to start. My colleague Jacob just sent me a few of the questions, so I will go through this and then see if I miss anything. So David asked, you need to manually write harness function for each function you want to fuzz, or is it generated automatically? Yeah, I think this was before I showed you that this actually can be done automatically. So yeah, this is one of the good things about our approach. You don't have to write a harness for each function manually. This would take a lot of time. Then we have another question from Christopher. How well does your mocking stubbing approach works in an AutoSAR setting? So it depends what exactly you mean with this question. So in the AutoSAR setting, I mean, we often have these different modules. Maybe you mean because in the AutoSAR settings, you require some very structured inputs. So what could help here is that you use some grammars to provide the, like, if you need data in a specific format. But generally, this approach should work the same in the AutoSAR setting. Another question from Christopher. How do you cope with automotive-specific compilers, say Green Hills, which could have instructions that are hard to port to Linux? What about your software includes pre-compiled third-party modules, e.g. shared object files, that can hardly be instrumented? Yes, so the approach that I showed you now will only test the software that you can actually run on Linux. So right now, this will not test for example, the hardware-dependent software that we need to simulate. You won't be able to test this because you cannot run it on a Linux. The problem is that this software, when you actually want to run it on the hardware that can be compiled on, this would be very slow. So usually that's not very feasible. And on the other hand, when you start just testing your software that you can actually run on Linux, then you already get a lot of findings. So this is like start with low-hanging fruits, and then the next step would be to think about, okay, how can we test those more specific functions? But usually when you start with this approach, you already have some work to do to fix the bugs that you find with this approach. Hope this helped. Okay, another question from Christopher. How do you check your findings or false positives? For example, your instrumentation could insert timing errors, or your mocks allow for a too broad data range. Yeah, so the good thing is that you can, when you found a bug, for example, with our tool, you can debug the finding, and then you can analyze if it's false positive or not. So, for example, in this last run, we actually had some findings. So, for example, we had a heap use after free, and our fuzzer saved the input that caused this crash. And now in this example, we could just start debugging it, and we could analyze, is this actually a real bug, or is it just, is it a false positive? Generally speaking, the instrumentation usually does not increase a lot of lag in your software. So if you are very strict time constraints, this might happen, but we didn't encounter this problem a lot. On the other hand, with the mocks allowing for a too broad data range, so this is the question: how do you fill in your mock Excel sheet? You could use the information from your API documentation. And if your API is documented, usually it should be written down what kind of data is expected. And if you want, you can restrict your mocks to only this data. For example, you could say this function can only return values from 1 to 5. And of course, you can again use the fast data provider to say, okay, consume an integer between 0 and 5. And then this function will only return the expected values. So if you have some false positive because of your mocks, you maybe have to use a little bit of manual effort to improve them. Another question from Harald. It seems to me a lot of work to set up a particular test. Is there a way to speed up the test creation by more automation? So I hope this question was also before I showed you how you can generate this this big fast test that we had in the end. But this is like exactly the problem that we encountered before. If you want to create a fast test for all of your functions, you have to think about a lot. And this approach actually gets rid of this problem. So in the end, it's not that much of effort anymore. Another question from David. What if you have more than one buffer instance as input to a function? Yeah, good question. So right now, the script that we wrote actually does not support it, but you could just like write your own script where you say, okay, the first one is data 1, size 1, the second one is data 2, size 2. So generally, the approach still works. It's just a question of how well do you want to write your script? How often do you have this? How many functions do you have in this of this type? Okay, another question from Jakub. Seems that within the XLSX, we simply rephrasing arguments and their types. This might be actually automated, in my opinion. Yes, that's correct. So as you saw, a lot of this was like just writing the same stuff. And especially if you return integers, this could be automated better. So we can still improve our script that we wrote so far. But on the other hand, when you have, in my example, all of the objects were of type struct, or at least struct pointer. But you could also have maybe enumerations. So it maybe not if you have a lot of if you have very different input parameters, you might still have to think about, is this an enumeration or is it a struct? But yes, there's still a lot of time that can, or a lot of stuff that can be automated even more. Okay. Another question from David. How do you know if an argument is an input or output? Okay. So usually, like if you see the function definition, let's take an example. So let's just take this function, of course. So this is the return value of the function. So this would be the output. And everything here are the input parameters with which this function is called. So this is easy to recognize. This is output. This is input. A little bit more complicated is if you have input that is actually, or if you have parameters that are pointers to data, because these can also be used as some kind of output, as I've showed you before. So this function output is int, but also the output in this case is the data that is written to this position and the data that is written to this position. So what you need to take a look at is the return value, and if there are any pointers that are not constant. So if they are not constant, then this function can potentially change the data where this points to. So you should always treat this as output. Okay. Next question. Jerome, what if the value is a data type, is a user-defined structure? I think we had this example, for example, here. This is like a structure that we defined. Also, what I said here, this is a very simple structure. Where you have to manually do some work is if you would have in this structure have some pointers to other data types, or for example, to some data on the heap. Because if we override everything in the struct, then overwriting pointers is not a good idea. But as long as your struct only consists of like the data itself, and not pointers to data, this can all be done automatically. David, how do you create an initial corpus for the mocks fuzzer? Yes, that's a good question, because with this mocking, we use our fuzzing data in many different ways. So, for example, let me show you here. We have our fuzzing data, and we use it. For example, we use it to determine how many iterations of this loop we will do. We use it to determine which function are we executing, and we also use it to determine what are the parameters. So there is not really a good way to use a corpus like for if you want to fuzz an image library, where you just take a lot of different images, use this as the corpus. So in our approach, it would make sense to maybe use a large corpus with many different binary inputs, and then let the fuzzer do his work on this. But yeah, generating a very good corpus for this approach is very hard. Okay, another question from Jakub. Is CI-Fuzz able to provide a list of functions from fast code that will require mocking? Okay, so this approach that I showed you right now is not integrated in our tool. As I showed you, we used scripts that we wrote around this. We will think about if we want to include this in the future. But right now, if you use CI-Fuzz, you will be supported by customer success engineers like me, and we will, of course, provide and use these scripts to generate these fuzz tests with you. Surab asked, would the approach for fuzzing a network protocol be different than the demo? I can use the network packet capture as an input corpus. Okay, it's like two questions. So if you fuzz software that requires some input via network, there are some ways to provide this input in an effective way. But then also coming back to the other question about the corpus, using network packets might be a little bit difficult here, because if you use our approach, you are using your Fuzz data not only as the parameters, but also for like the structure, which functions to call in which order. So what I would recommend here is more like use this surrounding, and then inside here tell your Fuzz data more specific how it should look like. So for example, if we have function 1 that should call a specific or send a specific network package or accepts a specific network package, then you might also use the Fuzz data provider or maybe a grammar to generate this packet from your Fuzz data. But yeah, so combining these two approaches, as I said, a normal corpus with our approach is not very feasible at the moment. Next question of Alan. Hello and greeting from Israel. Greetings back. I have a question. Is your solution scan inject unexpected abnormal input into the network and observe the results of abnormal output to find the system vulnerability? Thank you. So yeah, maybe also in this case, maybe our approach is, or this approach is not the best. So maybe it's easier to just write one Fuzz test to like send the network packages. And if you have the source code or the software that you want to test, of course you can use CI Fuzz to obtain the feedback and also to identify vulnerabilities. Okay, I hope this answered your question. Okay, then we have to come